Welcome to today's Explainer. For centuries, the atom was basically an impenetrable black box, just a complete and utter enigma. But today, we're diving into the ultimate scientific detective story. We're going to see exactly how some truly brilliant minds used ingenious experiments to crack open the fundamental building blocks of the universe. And that brings us to a really fascinating question. What actually happens when you try to break the unbreakable? The word atom actually comes from the Greek word atomos, which literally means uncuttable or indivisible. Historically, a brilliant scientist named John Dalton basically planted his flag on this idea with absolute certainty. He assumed atoms were the smallest possible things in the universe, solid, unbreakable, end of story. But what if he was spectacularly wrong? What if there's a whole hidden world inside that tiny sphere? Well, here is our roadmap for today's Explainer. First, smashing the indivisible atom. Second, finding the missing pieces. Third, shaping the modern atom. Fourth, by the numbers. And finally, the atomic family tree. Let's get right into it. Section 1, smashing the indivisible atom. Dalton's mistake. For years, John Dalton's idea of a solid, unbreakable sphere was pretty much the absolute gospel of chemistry. But eventually, that sphere was completely shattered. It literally cracked open to reveal a fundamental trio: the negatively charged electron, the positively charged proton, and the neutral neutron. Dalton's mistake actually became the ultimate catalyst for modern physics. The atom wasn't just a solid block at all. Actually, scratch that. It was more like a container holding even smaller, more basic pieces. Section 2, finding the missing pieces: electrons, protons, and neutrons. So how exactly do you measure an invisible phantom? It's like a giant puzzle. Robert Millikan's oil drop experiment is hands down one of the cleverest setups in history. He sprayed a mist of tiny oil drops into a chamber, zapped them with radiation to give them a negative electrical charge, and let them fall into an area with an electric field. By carefully adjusting that field, he perfectly balanced the downward pull of gravity against the upward push of electricity to make the drops hover, literally hover, in midair. Through this incredibly delicate balance, he captured the precise charge of a single electron. It's just an absolutely elegant piece of science. Because of Millikan's absolute mastery here, scientists could then calculate the mass of that single electron. And the number is truly staggering: 9.1094 times 10 to the negative 31st power kilograms. Just let that sink in for a second. You would need to write 30 zeros before you even got to the number 9. No way, right? It is so mind-bogglingly tiny, it's almost completely weightless compared to the rest of the atom. But the electron wasn't hanging out alone. By modifying a cathode ray tube, filling it with gas, and tweaking the setup, scientists observed a glowing stream of particles deflecting toward a negative plate. Because opposites attract, they knew for sure these had to be positive. Boom, they found the proton. Later on, scientist James Chadwick bombarded a sheet of beryllium with alpha particles and knocked loose a completely neutral particle that didn't deflect in an electric field at all. And with that, the neutron was finally brought into the light. Take a look at the mass of the proton and the neutron here. They are essentially twins, both on the order of 10 to the negative 27th kilograms. But compared to them, the electron is thousands of times lighter. Almost all the heavy lifting, the actual bulk of the atom, is carried by the protons and neutrons sitting in the core, while those incredibly light electrons carry that vital negative charge. Okay, section 3, shaping the modern atom, the great model showdown. So we had the pieces, but how did they fit together? Two dominant theories emerged, and a real scientific showdown kicked off. On one side, we had J.J. Thomson, who envisioned an atom with a continuous, uniform distribution of mass and charge. It was just a solid, happy little sphere. On the other side, we had Ernest Rutherford, who proposed something wild, chaotic, and totally revolutionary. An atom that was almost entirely empty space, anchored by a tiny, incredibly dense core. Thomson proposed what we affectionately call the watermelon model, though some folks prefer the plum pudding model. Imagine a nice, juicy red watermelon. Thomson thought the red, fleshy part of the watermelon represented a uniform sphere of positive charge. And the electrons, well, they were just scattered uniformly inside it, exactly like the black seeds in our watermelon. It totally made logical sense at the time. Everything was evenly distributed, solid, and stable. But then, along comes Rutherford with his famous gold foil experiment. This was a real game changer. He shot a beam of heavy, fast-moving alpha particles at an incredibly thin sheet of gold foil. Now, if Thomson's watermelon model was correct, those alpha particles should have just blasted straight through the soft, uniform positive charge like a bullet through tissue paper. And sure enough, most of them did. But a few of them deflected at really sharp angles. And incredibly, a very small number bounced straight back. Rutherford literally said it was as if you fired a 15-inch naval shell at a piece of tissue paper and it came right back and hit you. Bam! This completely destroyed the watermelon theory. So, Rutherford had no choice but to completely rewrite the rulebook and draw a new conclusion. Because a few alpha particles hit something incredibly hard and bounced back, he realized the atom absolutely must have a highly dense, positively charged center. He called this the nucleus, and because most particles went straight through without a care in the world, he concluded that the atom is overwhelmingly empty space, just a tiny, heavy nucleus at the center with electrons orbiting it somewhere out in the vast void. Now, to be fair, it wasn't perfect. Rutherford's model couldn't explain exactly how those orbiting electrons remained stable without just spiraling into the nucleus, but it was a monumental leap closer to the truth. Section 4, by the numbers, reading the blueprint. Whenever you glance at a periodic table or read chemistry notation, the secret code is actually beautifully simple. The Z at the bottom is the atomic number. This is the ultimate identity card of the element. It tells you exactly how many protons there are. The A at the top, that's the atomic mass. Remember how we said protons and neutrons carry all the weight? Well, A is simply the number of protons plus the number of neutrons. That is the heavy stuff, the whole shebang. Let's walk through this together and logically figure out how we find those elusive electrons using these numbers. In a perfectly balanced, neutral atom, nature absolutely loves symmetry. The number of negative electrons exactly equals the number of positive protons. But atoms often gain or lose electrons, becoming charged ions. If an atom has a positive charge, it actually lost some of its negativity. So you just subtract the charge number from the protons to find your remaining electrons. If it has a negative charge, it gained extra negative particles. So you add that charge number to the protons. It's really just simple bookkeeping, right? Section 5. The atomic family tree. Isotopes, isotones, and isobars. Just like you might share eye color with a sibling but be totally different heights, atoms share traits too. First up, we have isotopes. The crucial point here is that isotopes have an equal number of protons. They are the exact same element, they behave the exact same chemically, but they have a different atomic mass because they carry a different number of neutrons. Think of them like different models of the exact same car. One is just a bit heavier than the other. Next up on the family tree, isotones. Here's a quick trick. Look at the N in isotones. It stands for an equal number of neutrons. These are completely different elements with different numbers of protons, but they just so happen to contain the exact same number of neutral particles right in their core. And finally, we've got isobars. Isobars are atoms of completely different elements that happen to have the exact same total atomic mass. They don't share the same number of protons, and they don't share the same number of neutrons. But when you add their protons and neutrons together and throw them on the scale, the final weight is completely identical. Pretty neat, right? Let's lock this whole thing in with some real examples. On the left, we have chlorine-35 and chlorine-37. Both have 17 protons, because that's what makes them chlorine in the first place, but their masses are different. In the middle are isotones, sodium-23 and magnesium-24. Do the math with me real quick. 23 minus 11 is 12. 24 minus 12 is 12. They both have exactly 12 neutrons. And on the right, the isobars, carbon-14 and nitrogen-14. Completely different elements. Carbon has 6 protons, nitrogen has 7, but they both have a total heavy mass of exactly 14. We've covered an absolutely incredible journey today, from Dalton's unbreakable sphere all the way to the mathematical beauty of the atomic family tree. But before we wrap up, I want to leave you with this final, totally mind-bending thought drawn directly from Rutherford's discovery. We learned that the atom is overwhelmingly, vastly empty space. The tiny nucleus is really just a speck in a giant void. But everything is made of atoms. You were made of atoms. The chair you're sitting on is made of atoms. So, if atoms are mostly empty space, how solid are you, really? Seriously, think about that. Thank you so much for exploring the universe's building blocks with us on today's Explainer, and keep questioning everything.